Hello gentlemen, and welcome to section 6.7 Acids, Bases, Indicators, video number 3 for this section. Today we're going to do some calculations practice on using some of the equations that we looked at in the last video. So for our first equation, it says calculate the pH of solutions with, and for letter A hydrogen ion concentration equal to 1 times 10 to the negative third molar. So this is our concentration, and with this concentration I want to know what is the pH. So to do this, we use the basic pH equation, which is pH is equal to the negative log of times the concentration of, or the negative log of the hydrogen concentration. So I plug in my value for hydrogen concentration here, which is 1 times 10 to the negative third molar, and I plug this into my calculator. On the calculator, we have different buttons. I'll bring this closer so you can see it. So when we do this, we do the negative log. So negative button here for me, negative log, and I input my value. It's 1 times 10 to the negative third, close parentheses, equals, and I get 3. Now you might be asking, well, are significant figures involved in acid-base calculations? Yes, there definitely are. So in order to calculate the number of significant figures, we look at our sig figs in our given concentration. So our concentration has 3 significant figures. So that does not mean my pH has 3 significant figures. It means this. If I have 3 sig figs in my concentration, then my pH has 3 decimal places after my decimal. So 3.000. That would be my pH with the correct number of significant figures. Rewind that to see what I just said. Now B, calculate the pH of a solution with a pOH of 2. Now pOH is the power of hydroxide. In every solution you have H plus ions and hydroxide ions, OH minus ions. One of them is going to be in abundance, more abundance than the other, making the solution either basic or acidic. In this case, say I have a pOH of 2. This is not pH of 2, this is pOH. It's a different scale. So one way we can find this out very quickly is using this equation. pH plus pOH is equal to 14. 14 is a constant. This equation is a constant here. Well, 14 is anyways, and these numbers can fluctuate, but they have an opposite or inversely proportional relationship. So as one increases, the other decreases. So if I have a pOH of 2, I plug that in for pOH, and I want to know the pH, I can rearrange this equation, and pH is equal to 14 minus 2, and your significant figure rules for addition and subtraction apply here. This is your most precise but least precise number. You go by your least precise number, so you only have 2 significant figures here, but there's no decimal place. So your pH is simply 12. With the pH of 12, you know that this is a basic solution. With the pH of 3 over here, I forgot, this is an acidic solution. Now, different calculations. If I had a question that said calculate the pH of the solution with a hydroxide concentration of 1 times 10 to the negative 9th. That's negative 9th there. It's hard to see it now. Now, there's different ways that I can approach this problem. The first way I'm going to approach this problem is thinking of, well, how can I relate pH to the concentration of OH minus? That's the objective. Well, we know that pH is related to H plus. So it's the power of hydrogen, so it's the power of the hydrogen ions that are in solution. So I can use the relationship between H plus to get to pH. But I know that H plus and OH minus are connected through my equilibrium constant equation. This is my equilibrium equation with Kw. We learned that Kw is the equilibrium constant of water, and that's equal to the concentration of hydroxide and the concentration of H plus. And the product of those is a constant 1 times 10 to the negative 14th. So I can use this part of my equation to help me solve this problem. So Kw is 1 times 10 to the negative 14. I'm just reiterating that in this equation. So I can say, well, given this equation, I know that OH minus has a concentration of 1 times 10 to the negative 9th. So I put that in here, 1 times 10 to the negative 9th molar, multiplied times my concentration of H plus equals 1.0 times 10 to the negative 14. And that's going to be molar. That's our concentration there. And actually, it's not molar. Sorry. And I solve for H plus is equal to 1.0 times 10 to the negative 14th divided by 1.00 times 10 to the negative 9 molar. And I simply do that division using a calculator or using your mind, and you get H plus is equal to 1.0 times 10 to the negative 5th molar. I have 2 sig figs, so that's going to determine my sig figs there. But that's my concentration of H plus. That's not the pH. So now I have to do a second step and calculate the pH. So this is first step. Second step. pH is equal to the negative log of my hydrogen concentration. Hydrogen ion concentration. So I take the negative log of the value that I just found, 1 times 10 to the negative 5th molar. When I do so, I get a pH that is equal to 5. Now I look at my number of significant figures here. I have 2 significant figures, so I'm going to have 2 numbers after my decimal point. Now those are going to be zeros. 5.00. This is a pH of 5, thus this is going to be an acidic solution. I can do the same thing over here using a different method. Now we learned about pH, we also learned about POH. So given the concentration of hydroxide ions, I can use a different equation. I can use POH is equal to the negative log of the concentration of OH minus. It's different than pH, but it's still applicable. We can still use it. So POH is equal to the negative log of my hydroxide concentration. I'll get a POH equal to, if I did this out, 9. Significant figures, I have 3 significant figures, so I have 3 places after my decimal. So it's a POH of 9. But I'm not looking for POH, I'm looking for pH. The relationship between pH and POH is given by my equation of pH plus POH is equal to 14. I plug in my value for my POH, so pH is equal to 14 minus the POH, which is 9. So pH is equal to 14 minus 9. We get 5. In this case, it would just be 5 on the dot. And yeah, so pH is equal to 5. This is an acidic solution. Now, final example. If I were given a question, what is the hydrogen ion concentration present in a solution with a pH of 3.5? So now I'm giving you the pH, but I'm asking for the hydrogen ion concentration. We haven't done anything like this yet. So we have to solve for my concentration of H plus. Now we can't do this simply algebraically. We can't just divide both sides by negative log and then have our H plus isolated. Logs don't work that way. So what we have to do is get our negative side on this side. We can divide by -1 to get our negative on this side, and we get a negative pH equal to log times or log of concentration of H plus. Now to get rid of logs, we can raise each side to a power of base 10. Meaning this, I can say 10 to the negative pH. I'm raising this to a power of 10 equals 10 to the log of h plus. I just took this and I raised it to a power of 10, base 10. What this does, this 10 makes the log cancel out. They're like inverses of each other. It's like saying 1 divided by 10. So 1/10 times 10 divided by 1. So 1/10 times 10 gives you 1. So these reduce down to give you 1. So your new equation is this. 10 to the negative pH is equal to H plus. Document this in your notebook. This is your equation to solve for a concentration of H plus or the concentration of OH minus if this were in POH. Now you plug in your values. So I plug in my values here. I'll have, well, 10 to the negative pH. Well, my pH was 3.5. So 10 to the negative 3.5, you must put that negative sign there. If you don't, you will get an incorrect value. So 10 to the negative 3.5 is equal to my hydrogen ion concentration. I plug that into a calculator. When you do so, you get 0.00032. That's it. So H plus is equal to 0.00032 molar. If you want to put this in scientific notation, you would go 3.2 times 10 to the negative 4th molar. And that is that. So guys, please do these calculations. Take notes on these. If you have questions, please ask in class.